Dive right in here and get started on new stuff for the semester. So oh, there he is. How are you? So the syllabus for the semester is the same syllabus from first semester. Nothing changed there. You'll notice at the end I have the content for both semesters outlined. So that's all there. Nothing has changed, Ethan. Probably at some point you'd want to take a minute and look through the syllabus just so you're kind of caught up on that. If you have questions about anything, holler at me. But I'll kind of talk through points as we go throughout the year in addition. But all right. So the plan here for today is we're going to start chapter 8. I don't want to scare anyone, but this will probably be the most difficult set of topics we do for this semester. So if you have as much of an A game as you have, you want to bring it with us now. I'm going to go slow and make sure that we try to explain things pretty well. But this first section is going to be a lot of vocabulary and notation. It's going to be really important that you get comfortable with the vocabulary and notation pretty quickly, because it makes everything you're doing afterwards a lot simpler if you understand what it is we're talking about, right? So if I write something one way versus another way, that means something. You know, if we say certain words, that means you can do some things here and you can't do things other times. So the notation and the vocabulary are really important that we're doing a good job with straight away. Okay? I'll let you guys know that in the lessons here, chapter 8 has, let's look here, 3, 4, 5, 6, 7, 8 sections. We're only going to do the first half of this. I think we're only going up through section 4. Yeah. Just as a heads up, we're only doing the first half of this. We're not going to do anything three-dimensional in this class. That's where the really tough stuff is anyway, but we're only going to do 2D here. Anyway, so let's get started. Here we're going to be talking about vectors. In 8.1, we're going to be talking specifically about two-dimensional vectors. So a vector is a mathematical quantity or object that can be defined using two numbers. So the two numbers we need to represent a vector are a magnitude and a direction. So when we see magnitude, you want to think length. And when we see direction, you want to think angle. And vectors are a really important mathematical tool, as they're the primary primary object that you'll use in physics, right? Physics is describing how things interact in the real world. Super important branch of science. Most of physics is built around manipulating forces represented as vectors. So if you have any interest in, oops, come on. Oh my God, come on. It's been doing this to me today. I don't know what's the matter. There we go. So like a super important part of modern society, as most of the engineering done, the things that we've built have their basis in physics, which is all based around this idea of a vector. Now, there's lots of different ways to represent a vector. But one of the most common representations is going to be called component form. So when we write a vector in component form, we'll state the name of our vector. So in the textbook or in words, that would be using a bold letter. When I write it on my paper, I'm going to write the letter and I'm going to put that like half arrow hat on top of it. That symbol is talking about that this letter represented by V is a vector as opposed to a variable or a constant or some other mathematical object, that this is a vector. It's wearing the vector hat. And if that vector is represented in component form, we're going to use the wedged brackets. So geometrically, what that's saying is that I have a vector whose tail begins at the origin and whose head ends at the point A comma B. Everybody's okay with that idea? Just kind of introducing some vocabulary.
Could you say it one more time?
Sure. Yeah, so if I'm talking about this vector V in component form, that tells me that the tail of my vector is located at the origin, and the head of my vector is located at the point A comma B.
Oh,
So the length of that vector, that's the magnitude. The magnitude describes the length, how long that vector is. And the direction is going to describe that standard position angle, much as the same that we had from trigonometry, right? So far, so good. Just kind of talking through some vocabulary. Any questions so far? We haven't really done anything yet. We're just kind of naming some stuff. Okay. So when we talk about a vector in component form, we might also call it the standard representation for a vector. So again, those two terms could be used interchangeably. So standard form or standard representation and component form could be used interchangeably. They're talking about the same thing, just a vector described as, a vector whose tail is at the origin and whose head is at the point, in this case, A comma B. Okay. The magnitude of our vector denotes the length. And we have a special symbol for that as well. So when we talk about the magnitude of our vector, we're going to put two vertical bars around our vector to indicate we're talking about the magnitude. So this is a very common misconception. This is absolute value. This is the magnitude of a vector. How can I tell which one is absolute value and which one is magnitude? Yeah, the thing inside of it is wearing the vector hat, right? Now, when I type these things out, when I write them on a test or a quiz or in the homeworks or whatever, I'm not going to put the arrows on top of them. What do I do instead? They'll be bold-faced. So the vectors will be bold-faced like they have been so far, as opposed to wearing the vector hat. Is everybody okay with what I'm doing here? So I'm just kind of naming stuff and now coming up with some symbols to represent those things that we've named. Let me know if I'm going too fast. Can happily slow down or just even pause a minute for people that are still trying to catch up. Again, we're not in a big rush here. We can afford to do a good job. As I said before, like the vocabulary and the notation is important. So you want to make sure that we're clear, as like we're able to communicate clearly with one another when I write something or say something. You're able to know what that means, right? It's hard to do a problem if you don't understand like what the symbols are talking about or what the vocabulary is. Again, as we mentioned earlier, the direction of our vector is the angle, the standard position angle that basically the arrow is pointing in, right? So just like last semester, when we found, like cosine of 1/2 is equal to whatever, we'll be doing similar sorts of things to calculate directions now. So like solving a trigonometric equation, kind of that skill circles back. All right. Now, when we talk about vector operations in the next section, the first thing that we're always going to be doing is taking our vector and making sure it's in that standard representation or in component form, right? Again, component form and standard representation are talking about the same thing. Because the way we're going to do all of our vector operations, our vector arithmetic, is going to be based on things in vectors in component form, because it makes everything enormously simpler. So much simpler. So let's say that I have some vector and I have its tail at the point x1, y1, and its head at the point x2, y2. I'll call that vector V. What I want to do to get this into standard representation is I need to translate my vectors head and then tail so that the tail is now at the origin, but the distance between the head and the tail has not changed, or the angle between the head and the tail has not changed. So I need anything I do to the tail, I have to do to the head also. Is everybody okay with that? So after I've done that, my new component form vector, where is my head going to be at? Well, it's going to be at my new x coordinate started at x2, but I moved x1 to the left. Because I'm moving left on the xy axis, I should be subtracting. Similarly, if I look at the y-coordinate, my head started at y2, but now I've moved down y1. So now my component form version of vector v should be the x-coordinate from the head minus the x from the tail, comma, the y-coordinate from the head minus the y-coordinate from the tail. Or I can write it yes, Tia. So if it's going right, that means that like my tail would have been like over here, right? If I have to move this way. So this number was a negative, correct? So when it'll always like minus the negative will turn into adding. So if we write it this way as minus the tail, even if I have to move to the right, the negative signs will take care of it. Does that make sense? Okay. Good question, though. So it doesn't matter whether it ends up pictorially moving left or right, because the way we've set this up, it'll always just the signs will take care of themselves as long as we don't overthink it. So this method that we've just described is called the head minus tail rule. HMT just stands for head minus tail. Does everybody feel okay on what we've done here? Let's do an example, right? We all feel okay. So our example says, show that the vector from 3, -2 to 5, -1 is equivalent to the vector from -1, 2 to 1, 5. So when we say equivalent here, what are we saying? What does that mean? That they're really the same vector, right? So if I can show they have the same component form, that'll tell me that these are really the same vectors, they're just in different locations. If I can translate them both so that they have the origin as their tail and they end at the same point for their head, well, then they have to be the same vector, really. They're just two different locations. Everybody's good with that? All right, so my first vector I'm going to name AB. And now when I draw the arrow on AB, it's really important that I'm drawing the tail part of my arrow over the point that's the tail of my vector. And the head of my arrow is over the letter that's the head of my vector. So because it says the vector goes from A to B, I know I'm talking about that, right? Where this is my tail and this is my head. Does everybody see in the English language how I can tell that which one is the tail and which one is the head? It's a reading comprehension problem. Okay. So if I do my component form, it's head minus tail. So 5 minus 3, 1 minus -2. So my component form for AB is 2, 3. Feel good there? My other vector I'm going to name XY. Again, I'm going to take a minute and read and make sure that the tail is X and the head is Y, or that my arrow is pointing the correct direction. It is. And again, we'll do head minus tail, comma, head minus tail. And because they have the same component form, these two vectors must be equivalent. Feels good so far? No big deal, right? Okay. Let's talk some about magnitude and direction. So if I have a vector like this, and I want to find the magnitude of it, we told you the guys that magnitude was the same thing as length, right? So if I think back to geometry, what did I use to calculate the length of a line segment? If I think back to geometry, what tool did I use to calculate the length of a line segment algebraically? I used the distance formula. Do you remember that? That's all I'm going to do here. So the distance formula is the square root of the difference in the x's squared plus the difference in the y's squared. Everybody's okay with that? Mm-hmm.
So,
Mm-hmm. What's the important thing to remember about when you're plugging things into the distance formula? It doesn't matter if it goes, if you do 1 minus 2 or 2 minus 1, but you have to do the same in both spots. You can't do 2 minus 1 and then 1 minus 2.
and then also for the example that we did, they're equivalent, but the y for AB is -3 and the other one is positive.
Nope, they're both positive.
They're both positive.
They're both positive. That's okay. Now, question here. If I look at x2 minus x1 and y2 minus y1, do those look familiar, those quantities?
A plus minus, or
They are the component form, right? Or instead of doing this, if I took vector v and I converted it into a component form first, the magnitude of v is just going to be the components. So in the situation where you're given a vector as a head and a tail, typically what I like to do is I convert it into component form first, because if I have some vector in component form AB, the magnitude is just going to be the square root of a squared plus b squared. And that to me is like just neater to do it in 2 steps, because oftentimes that component form is going to be helpful in a bunch of different places. I like to just bang it out right at the beginning so that I can use it to make everything else simpler afterwards. Colby.
So the formula you just wrote under.
Yeah, we've just done that. We've just done the x2 minus x1 as a separate step to get to the component form. Whatever that answer is to x2 minus x1 is like my A. And then whatever that answer is for y2 minus y1 is like my B. Does that make sense?
Yeah.
Okay. So let's do an example here. Do some computation. All right. Find the magnitude for the following vectors. So it says vector u is in component form, right? How can I tell it's in component form? It says the wedged brackets. Since it's in component form, the magnitude for u, so I write the u with the vertical bars around it to represent the magnitude, is just the square root of 2 squared, or negative 2 squared plus 5 squared. Now, be careful when you're typing this into your calculator. The negative 2 needs to have a parenthesis around it. If you don't do that, you're going to get the wrong answer. So if I'm typing this into my calculator, I got to type it like that. So this would be the square root of 29, or if I wanted a decimal, approximately 5.39. Okay, let me show you on a second line here, Colts. So if I did instead, if I just did negative 2 squared and I didn't put a parenthesis around the negative 2, I'm getting the wrong answer. Because the calculator is going to follow the order of operations, which says exponent should happen before multiplication. So it's going to square the 2 and then make it negative. So it's going to give you a negative 4 there instead of positive 4. So you got to be a little bit careful with that. Here.
What was the representation that was on like the closed brackets? Would you call it yours your standard representation?
Or component form. Those mean the same. Those two words mean the same thing. Those two terms mean the same thing. Okay. Let's use a different color. Part B then says we have the vector CD, where C is this point and D is that point. So I'm going to first convert vector V into a component form, and then I'm going to do the magnitude second. So which one is the head and which one is the tail? C and D, first with C and D. Which one is the tail? C. How can you tell? Yeah, the tail of the arrow is over the C. So that's my head. So my vector V here is going to be negative 3 minus 4, comma, 1 minus negative 6. So then if I do the magnitude of V then, so that's the square root of 98, or approximately 0.9 or 9.90. And I guess you could simplify the square root of 98 if you wanted to, right? That's 7 root 2. That would be acceptable also. Since 98 is 49 times 2, square root of 49 is 7. So if you'd like to write it that way, that's also acceptable. So far, so good. Let's do some direction examples now. Okay. So to do the direction, we're going to do this kind of the same way that we solved for an angle in trigonometry. So the same way we solve for an angle using like our inverse trig functions, we're going to do the same thing here. So this question says, find the magnitude and direction for the vector v starting at 3, -3, so that's my tail, and ending at -5, 10, so that's my head. Regardless of what the question asks for, I'm always going to start, if I don't have a component form vector, by making it component form. Does everybody feel good there? It says magnitude and direction, so let's get the magnitude next, I guess. So 64 plus 49 is 113. And if I want that as a decimal, I could type that into my calculator. I'm just going to leave it as the radical, though, because that's, radical's fine. Now let's do the direction here. So I'm going to start by plotting my vector. So I have -8, -7. And we're going to be searching for this angle as my theta. Yes? Sure. So I'm going to then start by making this triangle with angle alpha. The side lengths of this triangle, well, the side on the x-axis needs to be the x-coordinate. The side on the y-axis needs to be the -7. And the hypotenuse needs to be the magnitude. Everybody so far so good? And I know that my theta is going to be 180 degrees plus whatever that alpha is. Does everybody feel okay there?
So the square root is it's not the opposite, it's like the other side.
It's the hypotenuse of the triangle.
Oh, all right.
It's the hypotenuse of the triangle. Is everybody feeling so far so good? Okay. So remember when we did this, to calculate our alpha, we did the tan inverse of the absolute value of y over x Notice that those are absolute values and not magnitudes now, right? Because we're doing the vertical bars around a number as opposed to a vector. Oi, Mr. Kulik. So when I type this into my calculator, I want to start by making sure I'm in degree mode. I am. And then I don't bother typing the absolute values in my calculator. I'll just do the absolute value in my head, right? So that gives me about 41.2 degrees. So then theta is 180 plus 41.2, or about 221.2 is my direction. Does that direction procedure look pretty familiar? Right? In fact, it's the exact same procedure that we did in first semester. Yes?
Why do we add the 180 at the end?
So if I'm looking for this angle theta, how far is it to here?
Oh, you gotta do the extra.
That's the 180. And then whatever that angle was, that's the alpha. Yes, Ethan?
So why do you need the hypotenuse?
I could have, if I wanted to do, say I did, instead of using tan inverse, I could have done sine inverse, and I could have done y over hypotenuse. That would have been fine. Still absolute values, but could do that as well. Yep, no reason you couldn't. I just always do tan, because if I didn't have to find the magnitude, I wouldn't have had the hypotenuse. If I use tan, I'll always have it from the component form, and that's all I need is the component. Colby. I would. Yeah. I would. Because the x and y are just the x and y from the component form. Easy. To me, that way. So, in general here, that direction is always going to be, you know, like some multiple of 90 degrees, either plus or minus tan inverse absolute value of y over x. So depending on what the picture looks like, just like we done, right? But it'll always be tan inverse of y over x that you're going to be either adding or subtracting from that multiple of 90 degrees. Really, I should probably say 180, right? Because probably nobody's going to draw it. A weirdo triangle there. Let's do that. 180. It'll either be 0, 180, or 360. It'll either be adding or subtracting. Feel good? Okay. So what if we want to go the opposite direction? What if we want to go from magnitude and direction into component form? Right? So in the previous problem, we went from our component form to magnitude and direction, right? What if we want to go the reverse direction? So here's the idea. So let's say we have our vector that has direction of theta and magnitude r. And what we're looking for then is like this point, x comma y. That point will be the same as the component form. Everybody agree? So if you think back to what we did in trigonometry, we know that that point is equivalent to some point on a circle, right? If that circle, if the radius is 1, this value is just cosine theta, sine theta, right? That was our definition for sine and cosine that we eventually landed at, right? They were just coordinates on a unit circle. So if our radius is instead 1, it's r, some number that's not necessarily 1, Well, we just multiply every coordinate by r on our circle, and the circle now has radius r. So what is that saying? Well, that gives us our formula that we're looking for here. If I have a vector with angle theta and magnitude v, then the component form is just v times cosine theta, comma, v times sine theta. Or I should say magnitude v times cosine theta, magnitude v times sine theta. That's it. It's our formula. Every single time. Woo! That's pretty easy. Let's do a quick numeric example. So it says find the component form for vector u, whose direction is 224 and its magnitude is 5. If I just follow the formula before, that's going to be 5 times cosine 224, comma, 5 times sine 224. And I just type it in my calculator now. Again, you want to make sure that you're in degree mode, since the angle that we're given is in degrees, but I did that already. But if you're pulling out your calculator for the first time and who knows how long, who knows what mode you left it in. How do you guys feel? So far, so good? That was a lot. Feels good for today. So your first problem set, which is due Sunday at midnight, all homework is due Sunday at midnight, turned into OneNote. Ethan, that's new for you. Is going to just be numbers 1 through 14. So if you look in the content library here on OneNote, all the problems are listed here. You can do them on a separate sheet of paper, or you can do them directly in your OneNote. Either is fine, doesn't make any difference to me. If you do it on a separate sheet of paper, you just take a picture of it and drop it into your homework tab on OneNote. If you have any questions about that, ask a classmate. Everybody's been doing it the whole semester, should be able to help you, or you can come talk to me. Either is fine. So you have, again, as a reminder, this Sunday before midnight is this first problem set 1 through 14. So on Monday I'll check them in. If you get marked as a missing or incomplete and you're like, ooh, I did that, you just need to make sure that the OneNote probably is synced through, or make sure everything is in order and send me an email, and I'll go back and recheck after you've synced your OneNote, and usually that takes care of everything. You have a week of grace to kind of figure that out before any late points start accumulating. But that's typically how the homework turn-ins work. Does that feel okay? It's pretty easy. All right. I'm done talking for today, so you guys can take the remaining 20 minutes or so and kind of get crack-a-lacking. If you're diligent, you can make a big dent in that 1 through 14 and have that much less to do later on.